This looks like a normal drilling operation, but it is not. Instead of drilling ahead, a conventional core is being cut. It will soon be retrieved to surface and taken to the laboratory for analysis. Welcome to PE 405, Core Analysis, the fifth in our series on well testing and sampling. In this module, we shall cover the why and how of core analysis, with some time devoted at the beginning to coring operation and core handling. After the core reaches the laboratory, you will learn how it is sampled and how conventional and special tests are carried out and complementary information recorded. Let's begin, though, with a few comments on the objectives of coring.
The first question we must ask is whether the sample is representative. And the questions are asked in two respects. Is the sample representative of the formation as a whole? You will find that we have more to say about the answer to this question in PE 501, Reservoir Environments. The second question is whether the core sample that we obtained at reservoir conditions, boxed and preserved and delivered to the lab for testing, is representative of the rock in the formation before we disturbed it. We shall have quite a bit to say about this question in this module.
But our drilling engineer and manager may ask a more overriding question. Why core at all? It's expensive. Our answer to this question defines the objectives of our coring program. There are both engineering and geological objectives for coring. Let's list a few of each. The engineering objectives include the definition of aerial changes in porosity, permeability, and lithology needed for reserve estimates and mathematical models. To define reservoir water saturation. To assist in the definition of net pay thickness. To assist in calibrating downhole tools. To provide data on residual oil saturation, especially for enhanced oil recovery studies. To supply rock samples for petrographic studies so as to define, for example, clay type and distribution. And to provide samples for special core analysis studies such as relative permeability, capillary pressure, and wettability. There are more engineering objectives, but these are the major ones.
There are a number of geologic objectives for coring. They include the definition of gas oil and oil-water contacts and reservoir limits, the collection of data for depositional analysis studies, the visual study of the core to define any fracture system, to provide oriented cores to analyze directional permeability trends, and finally, to analyze source beds to assist in exploration activities.
There are many reasons, then, for coring, and it is up to the engineer and the geologist to define at the very outset the coring objectives. It is only then that the coring program, including the list of tests to be run, can be specified and implemented. Now that you understand the objectives of coring and the need for careful planning, let's spend a little bit more time discussing the coring operation and then move on to core analysis, our major area of emphasis.
Most of us know that there are two major types of coring devices. Those run on drill pipe that give us a continuous sample of the formation cored, and those run on wireline after the hole has been drilled, which give us small samples usually spaced 1 foot or further apart of zones of special interest. The conventional coring device consists of an inner and outer barrel, approximately 30 feet or 9 meters in length. The barrels may be joined in multiple lengths for increased length of core recovery. In the J field, for example, it was common to run 3 lengths at a time. The bit is attached to the outer barrel. Conventional core barrels are typically 3 to 5 1/4 inches or 7.5 to 13 centimeters in diameter. The inner barrel is connected to the outer barrel by a swivel. This allows the inner barrel to remain stationary as the outer barrel rotates. As coring continues, the rock sample is pushed into and retained within the inner barrel by a core catcher. The core catcher allows the core to remain in the barrel during its trip to the surface.
In order to retain samples intact, especially unconsolidated samples, it is possible to use special inner barrels or liners. Thus, rubber sleeves, plastic liners, fiberglass, and aluminum inner barrels may all be used to retain unconsolidated cores. When the core reaches the surface, it is retained fully protected within the sleeve or liner as it is removed from the coring device and delivered to the laboratory. Here we see examples of a rubber sleeve, plastic liner, fiberglass inner barrel, and aluminum inner barrel.
In Canada's tar sands, we typically use plastic liners and freeze the core in the liner at the well site.
There are two more devices that can be used during conventional coring, the pressure core barrel and the sponge core barrel. Before discussing them, though, let's be sure we understand the concept of filtrate invasion and blowdown.
In most coring programs, the pressure in the wellbore is greater than the pressure in the formation. This will cause filtrate from the coring fluid to invade the reservoir rock and change the fluid saturation. This means that if the coring fluid is water-based, oil will be displaced from the core during coring and its measured saturation will be too low. If the fluid is oil-based, water will not invade the core and its laboratory measured saturation will be properly stated. A practical example is helpful. Here is the actual water saturation versus height in a reservoir. Note the level of mobile reservoir water. Now here is the water saturation distribution when the formation is cored with an oil-based coring fluid. And here it is when it is cored with a water-based fluid. The difference between the two represents filtrate invasion. We can draw an obvious conclusion. If you want an accurate water saturation, use an oil-based fluid. If you want an accurate oil saturation, use a water-based fluid.
In our company, we have a more specific policy. To determine residual oil saturation and preserve wettability, we use a bland, water-based mud with no surfactants, a pH of 8.5 or less, and an API filter loss of 3 to 5 cc's. For residual water saturation, we use an oil-based mud with physical properties close to oil, low surfactants, and low API filter loss.
Another operating phenomenon that affects the core results is blowdown.
Blowdown occurs during the normal retrieval of the core to the surface. Because there is a continuous reduction in pressure and temperature as the core moves upward, gas evolves from solution in the oil, expands, and escapes from the core, dragging oil and water with it. Unless something is done, the fluid volume loss can be substantial. There is one way to avoid blowdown, and another to measure its effects. By using a pressure core barrel, we can maintain reservoir pressure on the core throughout its recovery, and thus avoid the effects of blowdown. This is the preferred method for measuring residual oil saturations, for example, after water floods. The other alternative is to measure the effect of blowdown by using the sponge or foam-lined core barrel. In this case, oil is expelled from the core during retrieval, but it moves into the foam lining where it may be recovered and measured in the laboratory. The sponge core barrel is relatively new, but it looks promising, especially because it is less expensive than the pressure core barrel.
We now see that even in conventional coring, we must be sure to use the proper drilling fluids, the proper liner or sleeve, and if we need accurate saturations, a pressure core barrel or sponge core barrel in order to get complete samples and accurate results. Now let's move on and discuss wireline coring.
There are several different types of sidewall coring devices. This one is the most popular. It is referred to as the percussion sidewall and has hollow projectiles connected to the tool by a cable. The tool is lowered into the hole, and at the pre-selected horizons, the projectiles are fired into the formation face, and the tool is retrieved to surface. At the surface, the projectiles are cut from the tool, the plugs removed from the projectiles, placed in individual glass jars, and taken to the laboratory for analysis. The best data from sidewall cores is obtained from soft, friable to poorly consolidated sandstones. In hard rocks, the impact can pulverize the sample or break grain contacts. The sidewall drilled plug, a recent innovation in sidewall tools, drills up to 12 sidewall samples on a single run. Because impact is avoided, good samples from hard rock formations are possible to obtain.
Before going on to core handling and preservation, we should point out that considerably more detail is available in your manual on what we have just covered. You will find one table, for example, that gives the core dimensions for all of the various coring devices mentioned so far.
Once the core or core sample reaches the surface, it must be handled carefully. Then preserved, placed in containers, and shipped to the laboratory. Whole cores, for example, are removed carefully from the core barrel, wiped, and laid out in order. Total core length is logged and each foot or meter marked. Lost core is logged at the bottom of the cored interval, unless drilling times or mud loggers indicate it should be elsewhere. A brief lithologic description should be made by the well site geologist here, or later in the laboratory. The cores are then preserved according to the expected duration of storage and objectives of the coring program. For short-term storage, say 2 to 3 days, placing the cores in plastic bags or sleeves may be sufficient. Many other preservation techniques are possible, for example, wrapping in saran wrap and aluminum foil. Or, alternatively, submerging in liquids, canning, freezing, or coating with wax or strippable plastic. Each has its specific application and is more completely explained in your manual.
Cores recovered in rubber sleeves, plastic sleeves, and fiberglass protected cores are removed from the core barrel and then often cut into lengths of 3 to 5 feet or 1 to 1.5 meters, sealed with caps at each end and marked as to top and bottom depths. The cores are then boxed and shipped to the laboratory. A pressure core barrel is typically frozen at the well site, cut into 3 to 5 foot or 1 to 2 meter lengths, and shipped in a freeze box. Sidewall cores are removed from the metal projectile, placed in small jars, and sealed immediately. Depth should be recorded on the sample jar. Non-absorptive material such as foil or saran wrap may be added to the jar to prevent sample movement. Once the jar is closed, don't open it again until just prior to analysis.
Keep in mind that poor handling and packaging of cores at the well site can cause the core samples to weather, and improper labeling of boxes can cause great confusion at the lab.
So far in this module, we have learned why we core, how we core, what we must do to make sure we obtain a representative sample at the surface. Finally, we learned how the various types of cores are handled and preserved at the surface. Much more detail appears in your manual, and so, before going on to discuss core analysis, please stop the tape and read chapters 1 through 4 in your manual. They are not very long.